All right, Honors Chem, we are going to learn what dissolves what and why today. We are also going to learn about some of the heat that it will either be given off or taken up when we dissolve things and learn about the enthalpy going on there. And then lastly, we are going to learn how to deal with concentrations, specifically molarity and molality. Okay? So, first things first. We're going to look at how things dissolve. So in these pictures right here of these three beakers that I'm putting an orange box around, we are going to have time as we travel from left to right. Now notice we have a pretty big pile of salt here, and then the pile of salt gets a little bit less, and then the salt becomes completely dissolved. Now the process of dissolving the salt goes like this. If we look at water, if we draw the Lewis structure, we have an incredibly polar molecule. We have hydrogen bonds here. So these hydrogens are essentially almost a whole positive one charge. And this oxygen is almost essentially a whole negative two charge. Not quite, but almost. Those polar bonds are really, really strong. Okay, so this oxygen end is very negatively charged. And if we remember in salt, sodium chloride, we have the positive sodium bonding with the negative chloride. So if oxygen is negative, it's going to be attracted to the sodium ions in that salt. So let's look at what happens here. So if I look at oxygen, this oxygen side of this molecule is very negative. So yes, it will be attracted to that sodium. And water is a very, very small molecule. So if I can get a bunch of water molecules to join in and get the oxygen end oriented towards that positive sodium, they can actually break it free off of that sodium crystal, and eventually they will surround that sodium ion with all the oxygen ends of the molecules pointing in towards that positive sodium. On the opposite end, these hydrogens, because they're positive, they're going to be attracted to the chlorine. Okay, so if I can orient a water molecule so the hydrogens are attracted or towards that chlorine, and if I can get enough of these water molecules to do that, it will pull that chlorine away, and it will also encapsulate the chloride with the hydrogens all pointed in towards that chloride ion. And if I get enough water molecules to do that over and over and over again, pretty soon that salt becomes dissolved and it is totally in solution. Okay? So that is the process of dissolving. When we dissolve something, we are basically looking at the attraction between the solvent and the solute to interact with each other and pull things into solution. So dissolving is all about attraction between the solvent and the solute. Okay? So let's look at this next page. So we want to draw the Lewis structure for water. Okay? So we already did that on the previous page. We've got the two lone pairs. Okay? What type of water or what type of molecule is water? Is it polar or is it nonpolar? Hopefully you realize that because of those hydrogen bonds and the shape of it, we have a huge, huge dipole through that molecule. It is incredibly polar. Okay? Because water is polar, it is attracted to other particles with this property as well as ions, because ions have positives and negatives. So remember, opposites attract. So the positive end is going to attract negative ends of the neighboring molecules, and the negative end of water, the oxygen end, is going to attract the positive molecules of the positive ends of neighboring molecules. So, do you think sodium chloride would dissolve in a non-polar solvent? So think about this. If I have sodium, which is positive, and the chloride ion, which is negative, and I have something like methane that is completely nonpolar, right? That is completely nonpolar. There's no positive or negative end to that molecule. Am I going to get charged things to be attracted to non-charged things? Is that going to happen? No, it is not going to happen. Okay, let's try the iodine molecule. Remember, iodine is one of our diatomics. So iodine would be like this. Is iodine polar or nonpolar? Hopefully you realize that iodine has the same electronegativity as iodine. So those electrons are going to be shared completely equally. So iodine is completely nonpolar. So would iodine be soluble in water? So would I be able to get iodine to be attracted to something that has positive and negative ends? Because it has no positive or negative end. No. Okay? So nonpolar is not attracted. Nonpolar is not attracted to polar. Okay, so it would not be soluble in water. Okay, so let's draw the Lewis structure for carbon tetrachloride. So carbon tetra is 4, so we've got 4 chlorines. Okay, and all of these chlorines have 3 lone pairs on them. Okay, what type of a molecule is carbon tetrachloride? CCl4. What kind of molecule is that? Hopefully you realize that all those dipoles cancel out. So this is a nonpolar molecule. So would iodine be soluble in a solvent like carbon tetrachloride? Would I be able to get a nonpolar molecule to be attracted to a nonpolar solvent? Yes. Yes, because nonpolar is attracted to nonpolar. Okay, they will be able to be dissolved in each other. So nonpolar is attracted to other nonpolar molecules. Okay, would I be able to dissolve water in carbon tetrachloride? Remember, water is polar and carbon tetrachloride is nonpolar. Would that work? No. So polar is not attracted to nonpolar. Okay? So the easily remembered solubility rule is like dissolves like. Okay? So that means that if I have a polar or ionic solute, I am going to need a polar solvent. If I have, let's change the color. If I have a nonpolar solute, I'm going to need a nonpolar solvent. Okay? So if I want to dissolve something that's nonpolar, I need something to dissolve it that is nonpolar. If I want to dissolve something that is ionic or polar, I'm going to have to find a solvent that is polar. Okay? So like dissolves like. All right? I have attached a video to this module where it demos like, dissolves like. Okay, we're going to talk about some solution equilibrium now, and we're going to do some definitions. So saturated. What happens when something becomes saturated? If you've ever talked about saturated color, it means you can't put any more color into that. Or if I have a sponge that is saturated with water, I can't put any more water in that. So saturated is a solution that I cannot dissolve any more solute into. So the solvent has dissolved as much solute as possible. I cannot dissolve any more solute at a given temperature. Okay, I cannot dissolve anything more. All right? So, if that's saturated, what would an unsaturated solution be? Unsaturated means that there's still room to dissolve more. So the solvent has not dissolved. So the solvent has not dissolved as much solute as possible at a given temperature. Okay? All right. And then we have yet another definition. What's meant by supersaturated? So supersaturated. That's above. Super means above and beyond. So can I go above and beyond saturated? I can in very rare circumstances. So a supersaturated solution is a solvent has dissolved more solute than normally possible at a given temperature. Okay, and I am going to attach, let me make a note. I'm going to attach a video of a supersaturated solution to this module so you can see what it acts like and what it looks like. Now, you're like, how can I get something more solute than normally possible at a given temperature? Let's explain this. If we look at solubilities as a function of temperature, notice that pretty much everything becomes a little bit more soluble, except for rare things like this cerium sulfate. Everything becomes more soluble when the water is warm. So this is how I could make a supersaturated solution. What if I took a solution and I heated it up and I put as much solute as possible at the high temperature, and I slowly and carefully brought that solution back down to normal temperature without disturbing it? One of the things that has to happen for something to come out of solution or for something to crystallize is it's got to have something to crystallize on. So if I can keep that solution clean without any edges or any bumps to create a shock wave through that solution, I can keep it from crystallizing and that extra solute from falling out of solution. But as soon as I put a crystal in there or something for a crystal to start growing on, a shock wave through that solution, some kind of an edge where we can physically get some crystal to start forming, that extra solute is going to fall right out of solution. Okay? So, supersaturated solutions are really cool and they're really useful. And hopefully in class, I can show you some things that we actually use supersaturated solutions for. Okay? So, we want to talk about other factors that also affect solvation or the ability to dissolve something. So, if we agitate a mixture or a solution, if I stir things or shake it up, I can get things to mix pretty better, right? It moves the dissolved solute particles away from the contact of the surface and allows new collisions with more solvent and solute particles. So I can get more things dissolved in there. Okay, what if I increase the surface area of the solute, crush it up into a fine powder? It makes it so much easier to dissolve because I have a greater surface area allowing more collisions to occur. Okay? Think about putting a sugar cube into a cup of hot water versus powdered sugar. Which one dissolves faster? The powdered sugar for sure, because I have more surface area to create more collisions between the sugar and the water. Okay? And then raising the temperature. This increases the speed. Remember, temperature is a measure of kinetic energy. So if the kinetic energy is going up, that means the temperature of that solution is also going up. So that means the molecules are moving faster. If the molecules are moving faster, that also increases the number of collisions, which also increases the solubility. Okay? So here we go. Heat of solution. Some things are endothermic when they dissolve, and some things are exothermic. So if I take some ammonium nitrate, and I have a demo here that is in this module that you can see, where they take some ammonium nitrate and they dissolve it in water. Remember, AQ means dissolved in water. This will break into its ions as it dissolves in water. And as it dissolves in water, you will notice in the demo that the temperature goes down. And because the temperature goes down, you know that it's absorbing energy from the surrounding materials. So that means that it is endothermic. Okay? So it is endothermic. It is absorbing energy. Okay? So if it is absorbing energy, we put the delta H on the left-hand side, right? So we're going to put the delta H on the left-hand side because it is an endothermic reaction. Remember, endo goes on the left side. Exothermic, as we're releasing energy, it's going to feel hot. We're going to put on the right side because it's a product. Okay? So what would happen if we heated this up? What would happen if we heated this up? That's the same as putting more heat into this situation. So if I put more heat into this situation, wouldn't it make this side really, really heavy? Right? I would have a lot of heat on my reactant side, or a lot of weight. So how do I get this to level out again? I have to make more products. So if I have to make more products, this is going to shift to the right. Okay, this will shift to the right. Okay, so if this shifts to the right, it makes more ions. So the next question is, would ammonium nitrate be more soluble in hot or cold water? Well, if it's shifting to the right to make more ions when we heat that water up, isn't that the dissolved side? So if it is warmer water makes more things dissolve, this would be more soluble in hot water. Okay, so we would have ammonium nitrate be much more soluble in hot water than in cold water. And you'll see that if you've ever used one of those instant ice packs, that stuff dissolves really well the warmer it gets. The more you put that instant ice pack on your whatever's been injured, the more that ammonium nitrate salt creates and gets dissolved, okay, if you've ever used one of those. All right. And this is not, okay, so this is going to shift to the right, and it still wants to think. Okay, and it's going to be more soluble in hot water. All right, next, hopefully we can get my computer to stop thinking. Next, we're going to dissolve sodium hydroxide. And if I'm not going to, I might try and find a demo for you on this. Let's see, sodium hydroxide in water. This is a fairly dangerous reaction to do because sodium hydroxide creates a lot of heat when we put it, and it creates a really strong base that can really splatter and splash at you and burn you pretty well. So I usually don't do this demo. I will find a video for it if I can. So this creates a lot of heat. If I dissolve sodium hydroxide, it creates a lot of heat. So we're going to put exothermic. It gets hot. So this is a very exothermic reaction. Okay? Excuse me. All right. So this reaction is extremely exothermic. This gets really, really hot very quickly. So because it's an exothermic reaction, we're going to put the delta H on the right side of the equation. It is a product. Okay? So what would happen if we heated this reaction? Okay? So if I added more heat, that would make this reaction go like, let's see, it would make the reaction, it would make this product side really, really heavy, right? That product side would be really heavy. Yeah, product side, heavy. So if the product side is super heavy, we are going to need to make the reactant side heavier to get it back into equilibrium. So we are going to have to shift left. So the hotter we make this, the more sodium hydroxide actually becomes less soluble. It becomes less soluble the hotter we make it. So is sodium hydroxide more soluble in hot water or cold water? It is definitely more soluble in cold water. Okay, and in fact, you want to do this in cold water because it generates a lot of heat. Okay, so let's look at this one. How does an increase in temperature affect the solubility of gases dissolved in liquids? So CO2 in gas form versus CO2 in water. This also is exothermic. Okay, so this means that if this becomes really, really hot, we're going to have the CO2 become gas and go out of solution. So why do trout go into deep water in the summertime? What is it about deep water? The deeper the water, the colder it is, right? So if I create colder water, I will go this way, right? So it will be more gases will be dissolved in the colder water. More gases are dissolved in the colder water. Okay, and if you remember, the gas that we're really interested in keeping the fish alive is dissolved oxygen. Those gills have to get the dissolved oxygen out of the water. Okay? So if we want the trouts to survive, we want to keep that water nice and cold. Otherwise, they will not have enough oxygen to breathe. Okay? Then why do catfish, bass, and perch survive well in Lake Powell? Lake Powell is pretty warm. I don't know if you've ever traveled down there in the summer. By the end of the summer, it is pretty warm. But if I put a trout in Lake Powell, it would not survive. It would actually go belly up and suffocate because it doesn't have enough water or enough oxygen to breathe. But if you've ever seen trout and bass and perch, they're not nearly as lively as trout. They kind of are slower fish. They don't use as much muscle, not as much. They don't swim nearly as quickly. So these are kind of, not very active fish. So they don't need as much oxygen, where trout are very active. So they need a lot. I know that should be 2 words, a lot of oxygen to breathe. Okay? Now think about this. If I put a can of a liquid and I increase the pressure on here, so I increase that pressure, is it going to do anything to affect the solubility of solids and liquids? Nope. So pressure does not affect the solubility of solids in liquids at all. But what about gases? How many times have you opened up a pop, there's my Midwestern accent, a soda, you guys call them soda out here. How many times have you opened up a soda out here and heard that pressure, whoosh, that whoosh? They pressurize that soda can so that they can keep the gas in solution. And once you open up that soda can, you're releasing that pressure and the bubbles all of a sudden come out and it becomes carbonated. So the higher the pressure above that liquid, the more soluble the gas is. Because the higher the pressure on top of that soda can, the harder it is for those bubbles of gas to actually push against that atmospheric pressure. More pressure, harder it is for those gases to escape, so they stay in the liquid, stay dissolved. All right, solution concentration. We're going to discuss a couple mathematical ways of expressing solute concentration. The first is weight percent. You're definitely going to want a calculator for this. Okay, definition is the mass of the solute divided by the mass of the solution times 100%. This is what we call a weight percentage. There are some things in the drugstore that are done by a volume weight percentage and others that are done by a volume percentage. Okay, so this is a weight percent. Okay, there's all kinds of different ways we can do percents. So let's calculate the percent weight if I have 15 grams of copper 2 sulfate dissolved in 150 grams of water. Okay, you guys know how to do percents, so let's give it a go. Okay, so the solute here is my 15 grams of copper 2 sulfate. So 15 grams of that copper 2 sulfate and the total mass of the solution. What is that solution made up of? It's made up of the 150 grams of water, and it's also made up of the 15 grams of the copper 2 sulfate. So I'm going to take 15 divided by 165, and then I need to multiply it by 100%. Okay? So when I do that, I've got 3 sig figs I get 9.09% weight. Okay? So how many grams of sodium chloride are there in a 15% solution that has a mass of 325? So what's 15% of 325? How do I figure that out? I can do this two ways. 325, let's see, is equal, so I can just multiply that by 15% in a decimal form. So if I make 15% in a decimal form, it's just going to be 0.15. And I would just take 0.15 multiplied by 325. Okay, and my computer wants to think some more. How frustrating. Okay, so if I get this in a percent as a decimal, this is going to be 0.15. Okay, so 0.15. And if I do that in my calculator, I get 48.75, but I really only have, this has 3 sig figs, so 1, 2, 3, that 5 tells me to round up. So I would report this as 48.8 grams of sodium chloride. Now there's another way I could set this up as well that's a little bit more complicated. So I could set this up as an equivalency. 15 over 100, which is what 15% means, is equal to something over 325. Now, if you'll notice, when we solve for x, we will get this kind of an equation right here. Okay? It's just a different way of looking at it. Okay, mole fraction. Mole fraction, the definition of mole fraction is the moles of component. Let's see. Let's actually it's the number of moles component over the total number of moles in the solution. Okay? So you have to do a lot of mole work, okay? So let's find the mole fraction of sodium chloride and water if I have 350 grams of sodium in 1,000 grams of water. So the first thing I have to do is figure out moles of each. So let's take the sodium chloride first. So I have 350 grams of sodium chloride, and I need to find how many grams of sodium chloride are in a mole of sodium chloride. So sodium is 22.99 and chlorine is 35.45. So when I add that up together, I get a molar mass of 58.44. Okay, so when I do the math there, I get 5.99 moles of sodium chloride. Okay, I need to do the same thing for water. So I've got 1,000 grams of water, okay, and those are all significant. And 1 mole of water, let's see, 2 hydrogens plus an oxygen, 18.02 grams of water. Okay, so when I do the math on that, this will give me 55.49 moles of water. Okay, now remember, it's the mole of the solute, which is the sodium chloride. So I'm going to take the moles of the sodium chloride, divided by the total moles. So I have the 55.49 moles of water plus the 5.99 moles of the sodium chloride for the total moles. Okay, so 55.99 divided by the sum of 55.49 plus 5.99 gives us a mole fraction of about, let's see, 0.0974. That's our mole fraction of sodium chloride. Now I could find the mole fraction of water by doing the opposite. I could do 55.49. So if I wanted to do the water, it would be 55.49 divided by the total. So 55.49 plus 5.99. This would give me the mole fraction of water, and that would be 0.903 mole fraction water. I should put fraction here. Okay, so we can do it for either the solute or the solvent, either way. Okay, so here we go. Molarity. Molarity, this is the most important concentration that we use. We use it all the time for the rest of the year. It is moles of solute divided by liters of solution. Okay, this is the one that you really have to get your mind around. We're going to do a couple of examples of these. Okay, so I want to find the molarity of a solution by dissolving 82 grams of calcium nitrate in 500 milliliters of solution. So the first thing I've got to do is I've got to get these grams into moles, right? That's my solute. And I have a volume of solution here, okay? So I need to get my solute into moles. So I'm going to take my 82 grams of calcium nitrate. Okay, I need to find my molar mass of calcium nitrate, right? And if we add up calcium is 40.08. Nitrogen, we've got 2 of them, 14.01. And oxygen, we've got 6 of them, times 16. We add all of that up, we get a molar mass of 164.10 grams, right? So per mole there. So I have 164.10 grams of calcium nitrate in 1 mole of calcium nitrate. Okay, so my grams are gone, and I have moles on top, which is what I want. Now I need liters of solution. I have milliliters, 500 milliliters of solution, right? Now, I don't want milliliters, I want liters. So isn't there 1,000 milliliters in 1 liter? So my liters cancel out, my milliliters cancel out, and I have liters. So I have moles per liter, which is what I want. Okay, so I'm going to do the math here. I'm going to take 82 divided by 164 divided by 500 multiplied by 1,000, and I should come out, I got 3 sig figs on all of these, right? At least 3 sig figs. So this will come out to 0.999 moles per liter. Now there is a shorter way of doing the units. Instead of writing moles per liter, we've decided that molarity can be shorthanded with a big capital M. That big capital M means moles per liter. Okay? All right. I want to do this example 10. We're going to come back next time and do examples 8 and 9 later. Okay. Actually, I probably want to do, let's see. I probably should do 9 first. Let's do 9. How many liters of a 0.5 molar solution, that big M is pronounced molar, molar solution can be made from 80 grams of sodium hydroxide? So what we want to do is we want to end up with liters on top, right? So we're going to start with our 80 grams of sodium hydroxide, and we want to get it into moles, right? So if I have a sodium, 22.99, oxygen is 16, hydrogen is 1.01, I add that all up, I get 40 grams of sodium hydroxide per 1 mole of sodium hydroxide. Okay? Now, I want volume on top, right? Can I use this concentration? Isn't this 0.5 moles of sodium hydroxide in 1 liter of solution? Isn't that what that means? So can I use this to cancel out moles and get into liters? I definitely can. I can put the moles on the bottom and I can put the liters on top. So I need 0.5 moles of sodium hydroxide in 1 liter of solution. Okay, so my grams cancel, my moles of sodium hydroxide cancel, and I'm left with liters. So 80 divided by 40, which is 2, divided by half is 4. So I will be able to make 4 liters of a 0.5 molar sodium hydroxide solution with that. Okay, and example 10. What is the molarity of a solution of hydrochloric acid if the density of the solution is 1.12 grams per mil and the solution is 25% weight HCl? So what I want you to do is I want you to pretend that you've got 1,000 grams of solution. And here goes my computer again. Okay, so if I have 1,000 grams of solution, what's 25% of 1,000 grams? It's 250. So I'm going to have 250 grams of hydrochloric acid in that 1,000 mils of solution, or that 1,000 grams of solution. Okay, so hopefully I can start writing this pretty soon. Okay, so 25% of
I can learn to understand you much better if I can.
25% of 1,000 grams is 250.
Yes.
So I'm going to have 250 grams of hydrochloric acid in 1,000 grams of solution. Okay, so we want moles per liter. So I'm going to get my hydrochloric acid into moles. So the molar mass of hydrochloric acid is 40. No, it is not 46. Okay, so 35.45, 36.46 grams of hydrochloric acid will give me 1 mole of hydrochloric acid. Okay, so I now have my moles on top. So moles per liter, right? We want moles per liter. So I've got my moles on top. I just need to get liters. So can I use the density to transfer from grams to liters? I have grams to volume. So I'm going to put this on the top, 1.12 grams of solution in 1 milliliter of solution. My grams of solution cancel out, and I now have milliliters. I can definitely convert milliliters. I have 1,000 milliliters in 1 liter of solution. So my milliliters of solution cancel, and I'm now into liters. So I have moles over liters. Okay, so when I do this, I can actually, 1,000 divided by 1,000, I can actually kind of get that to cancel out. So I'm going to take 250 divided by 36.46 times 1.12. This will give me a molarity of 7.97 moles of hydrochloric acid per liter of solution. Or I could use a big capital M and just say molar HCl. Okay? One more example here, molality. Molality is number of moles of solute divided by kilogram of solvent. So we're not doing volume. We're doing moles over kilogram of solvent. So calculate the molality of a solution with 15 grams of ethanol in 350 grams of water. So let's take our 15 grams of ethanol, and we have it in 350 grams of water. Okay, this is our solute, and this is our solvent. Okay, so the first thing you've got to do is figure out what your solute is and what your solvent is. Now your solvent, you need to get into kilograms, and your solute, you need to get into grams. So let's work on getting our solute into grams. So if I look at ethanol, ethanol has a molar mass of 46.08 grams of ethanol in 1 mole of ethanol. Okay, so my grams are going to cancel, and I'm now into moles. So I've got the mole part. Now I need to get into kilograms. Remember that I have 1,000 grams in 1 kilogram. So 1,000 grams of water will give me a kilogram of water. So my grams of water will cancel out too. So I now have moles per kilogram. So if I do this, let's see, 15 divided by 350 divided now by 46.08 times 1,000. This gives me, let's see, I've got 3 sig figs. This gives me 0.930 molal ethanol in H2O. Now, to make it even more confusing, molality, molal, is given by a lowercase m. Okay? So, I don't know why they chose such similar words and such similar shorthand, but that's what they did. So we will practice more of these next time and also teach you how to do dilutions. So have a great day and happy calculating. We'll see you later. Bye.